And hey, good morning. Week and a half, right? That's what we got left. I just want to say a couple words about the midterm and what we've got for the rest of the semester, what topics we're going to be talking about. The first thing I want to do is share with you the Canvas site. Canvas. Where are you? There's Canvas. Share. Hopefully, you're looking at this screen right here. Um, First thing on the midterm is let's see. I'm going to post the solutions to it. It'll probably be right after homework 7 here. There's midterm 1 solutions, midterm 2 solutions will show up here shortly. Um, that's what I want to do, so you can review that, use it for the final. The final will mostly be chapters 4, I guess, pretty much predominantly chapter 4. I haven't decided if we're going to move into perturbation theory or not. If we do, that'll also be on the final. So it's all of this stuff and what we're talking about today. And I thought I'd uploaded these over the weekend. This is the tutorial for today. I'll be going through some of it. It might help you to open it up or even print it out if you can. And then there's 2 handouts, spin and change of basis, that are pertinent to what we're going to be talking about both today and on Wednesday. Okay. As we move forward to the end of the week, we're going to be talking about the interaction between these electrons and magnetic fields, and maybe even a little on electric fields too. So we'll be talking about that. And also, and this is, I haven't decided which topic we're going to do next week. We'll either talk about adding up angular momentums, or we'll talk a little bit about perturbation theory, because everything we've talked about so far throughout the course of the semester, these are problems that people have come up with solutions that you can do. You can actually, you might not like it. You might not like series solutions to differential equations. You might not like the algebraic method with raising and lowering operators, although once you've worked with those, you come to think they're really good things. You may not like solving eigenvalue equations using linear algebra techniques. You might not like all of that, but I think it is important, and the problems are doable. What do you do when you get some sort of weird potential that there is just no technique that anybody has developed or that you can develop to solve that thing? And the answer is you make approximations, and perturbation theory is a method of approximation. And I haven't decided if that's more important than actually looking at combining the types of angular momentum that we're going to talk about today. Okay, so that's the kind of the schedule for the week. If you look today, the hydrogen 2 tutorial is due. Wednesday, the angular momentum tutorial that we finished up talking about angular momentum on Friday, that tutorial for that material is due Wednesday. I'm thinking I'm going to make spin due Friday, but I may make it due Monday. I'm thinking Friday because there is a homework assignment coming on chapter 4. And that'll be out probably tomorrow is when I'll get that out to you, and that will be due next week. And so if you start pushing too many things till next week, the semester has to end sometime. And so I'm a little worried about doing that. 1 tutorial a day is probably a good pace. Okay, so anyway, stop sharing this with you. I want to say a couple words about the midterm exam. First of all, a number of people did extremely well. 3 perfect papers, a near perfect paper, let me share with you my, yeah, there it is. Share with you my PowerPoint because I want to be able to make a couple notes here. And a couple solid A's, solid B pluses. And my one advice to people who didn't get the grade that you were hoping for, and that is the advice is documenting your solution a little better. And because I think that's where some people lost points. I think those that did pretty well, I mean, about half of you recognize that not only did you do well, but you should have had a lot of confidence from some of the questions that were asked that, yeah, that's got to be the right answer. Okay. You get results and you go, okay, well, those eigenvectors are orthogonal. Yep, that works. Those 2 matrices multiplied together did give you the identity matrix. When you transformed your operator matrix into a basis of its own eigenvectors, all of a sudden the eigenvalues turned out to be the diagonal matrix elements. How cool is that? The determinants of the 2 were the same. The trace was the same. All of those little hints along the way made you have confidence that your solutions were correct. And I think some of you said, I know the answer to this. There's no doubt I got it right. And if the math wasn't working out for you, and you weren't seeing that the determinants were the same, the traces were the same, it's incumbent on you, of course, to go back and find your algebra mistake or your, in many cases, arithmetic mistakes. And so that's my first pitch. If you had points taken off, it was sometimes because I just couldn't follow your work. And sometimes you would jump to something. I'm go, well, I know what I had to do to get from point A to point B. Where is that? Okay, and you'll see words like how or why or where on your paper. If you have like another sheet of paper or something, or an explanation of how you got from point A to B, feel free to resubmit it to me. I'll take a look at it. There were times where I was a little concerned. I'm like, okay, where'd that come from? It just shows up. It's right. But you have to understand that an upper level physics course, it's a little different from, the 111, 112 courses where the emphasis was kind of on the right answer with units. Now the emphasis is on the work behind behind the answer, and making sure that those concepts are firmly in place. Okay, I think some of you, it was pretty clear, tried to use Wolfram Alpha. Oh, come on, internet connection. This happened about 3 times to me in my morning class. Hopefully it's back right now. It seems to be back stable again. If I freeze up, my apologies. Watch the video, because that's always good. In any event, I saw people trying to use Wolfram Alpha, a couple notes on it. Not as many as I would have thought, though, people saying they were using Wolfram Alpha. One of the things you'll notice is that, and I did not kind of push Wolfram Alpha when we were doing the matrix solutions. Wolfram Alpha will give you an eigenvector. In fact, it'll solve the complete eigenvalue problem. You just literally type in the command with your operator matrix, and it'll find your eigenvalues. It'll find your eigenvectors. It'll try to. There's a way to make it do similarity transformations to transform the operator matrix into a basis of its own eigenvectors. The one problem I'll tell you about Wolfram Alpha, and it's why I didn't push it. The eigenvectors that Wolfram Alpha provides for you are not normalized to 1. If you think about it, that's something that we do as physicists use in the study of quantum mechanics, because it's necessary to normalize our eigenvectors, because the square of those eigenvectors is a probability for us, and we need the total probability to be 1. Just a mathematician doesn't have that requirement. The eigenvector squared doesn't turn out to be any kind of probability, so there is no requirement for them to be normalized. And so I think some people got kind of caught up. There were a couple of people that had solutions where I'm like, well, that eigenvector is not wrong. It's just not normalized. Where did it come from? Those are the kind of questions that cause people to lose points. And so if you got something to resubmit to me, feel free, send me an email with any explanations. Maybe there'll be some what we called reclama points when I was in graduate school, and you can get some back. By and large, I think everybody's on track here. I mean, if your goal is a P for pass, I don't think anybody's failing. But if you want to expound on some of what you did, because I took points off with a why or where question, feel free. I mean, I'll take a look at it as time permitting. I do want to make one technical point on complex numbers. And, one of the things that I find a little different here teaching at Washington College is that, the math that you've taken is sometimes not as complete as a physics major might have in another physics program. And that's the nature of our liberal arts degree. And it's perfectly appropriate for a liberal arts degree, but the ability to have proficiency in complex numbers. Oh, come on back. I thought I had the pen activated here. In complex numbers, nope, still no pen. Go back. Pen, there it is. Now I got a pen. Okay, proficiency with complex numbers. Remember, anytime you do this to a complex number, okay, you do that operation, that means multiply by its complex conjugate, generally in this order, okay, but that's an important piece. And so, for example, when you're doing the reflection coefficient, and it's, I think the coefficient we had reflected back divided by the coefficient that was going in, railroad tracks squared, that means you multiply by the complex conjugate. Okay, and some people didn't do that, and that is an important step, and it was victory or defeat on the last question in problem one, where you had energy less than the barrier height. Okay, you should have said, well, if the energy is less than a barrier height and it's an infinitely long barrier, well, there can be no transmission through it. I need a reflection coefficient of one. That should have been the sensible answer, and people were getting something other than one, and it's because they didn't do this step. Similarly, in problem two, when you had to check if something was normalized or even simplified, remember the multiplication is often something like this, right? A, B, and that would be, of course, A conjugate, B conjugate, right? And if one of those has got an I, you got to put in a minus I specifically to do it. And the other thing I guess I would point out related to that is this showed up as a term an awful lot when you did something like multiplying by a complex conjugate. Um, you saw as you were simplifying your expressions in problem two, okay, you should have had this show up a lot. I just want to point out the answer to that is two, and has been since I was an undergraduate taking a math class, and it still is today, right? One times one, and then the i's are also plus one. One and one is two. And that, I think a lot of people left expressions like this, and I'm like, okay, you need to simplify that. And if you insist on writing that, you're going to have a mess that you're not going to be able to interpret. And of course, I'm going to have a hard time grading. If you simplify with that, and you saw, oh, that often went with a normalization constant of 1 over the square root of 2, which squared, okay, and so that often canceled, and it made things simplify real nice. But if you couldn't see to simplify something like this, that ran you into trouble. Okay, so those are just some generic comments on the second midterm, things that I saw more than just once, and so I just wanted to point it out to everybody. I did get asked a question about homework 2 and 3, which I have to be embarrassed about because they're not graded. I still have them all. If you want your original papers back on anything that you turned in before the break, it's very likely I'll never see any of you again face to face to hand your paper back to you. If you want it, let me know. I splurged and bought one of those high speed sheet feeders, and I can scan the document in and send it back to you. But one of the things I've found over the years of teaching is people turn stuff in and they really don't want it back. At the end of every semester, I have a stack of papers that I've tried to hand back and were either left behind or nobody ever wanted to claim. But if you want those, I can scan them in and send them to you. And so I just offer that up. All right. Any questions for me on any of that? All right. Great job to the 3 perfect papers. There was a near perfect paper, like I said, a number of nice A's and solid B pluses. Okay. But if you weren't in that range and you want to be, okay, my only advice is a little more documentation. I will say just one other thing. The humanities people have got us all convinced that you don't submit your rough draft of a paper, right? In fact, a lot of humanities professors have taken to making you submit your rough draft, making you submit your outline even, okay? And then they send it back to you with comments, and then you send in your final draft. I'd argue you could consider that same technique in some of your physics assignments moving forward, especially in the upper level class. I think it's a mistake to expect that you're going to get it exactly right on the first time through. I think I told you on one of those tutorials, I knew roughly what the right answer was supposed to be, and this was the one it was when I was doing the Graham-Schmidt process in order to take a set of basis vectors that weren't orthogonal and turning them into orthogonal basis vectors. I kept making mistakes. I had to go through it 3 times before I finally got it right. And although quantum mechanics is not my research field, I've been doing physics for a long time, and it still took me 3 times through that problem. And that's just part of life. That's why our midterm was only 3 problems. And oh yeah, by the way, on those, is this Hermitian? Is it not Hermitian? If you go through the reading at the start of chapter 3, a number of those questions were sort of answered. Okay, maybe the one that was a little unique, I thought, was when I asked you about the derivative with respect to time. But I gave you some hints for that. And if you don't use the hints, you do that at your own peril, because I'm telling you, this is the answer, right? Go this way. All right. Anyway, on to today's topic, which is spin, which is to a great extent just a special case of the angular momentum that we were talking about last week. Okay. And we'll do some review on that. I've got almost an equation sheet made up, but I just want to take you back to classical mechanics. I guess most of you had Kaiser for that class. And if you're looking at orbital mechanics, which I think is probably a chapter in the advanced mechanics class, you learned about angular momentum for something orbiting, and then something at orbiting might also be spinning. And so that's why I got this little graphic of the moon going around the Earth here. And if you wanted to calculate the orbital angular momentum, you do something like that, where of course R is just that distance right there. Okay, it could be an elliptical orbit, in which case R might be changing a little bit as it goes around. And then the momentum P of this thing about that axis. So there's the momentum. Okay, so that's great. But as you all probably know, the moon is also spinning. It's kind of coincidental that it's spinning with exactly the same period that it revolves, but it has a separate rotational motion because it spins on its own axis. And, we usually write that as a moment of inertia times the angular velocity of the thing that's spinning around. But, you could argue that that's really nothing different from just another form of the regular angular momentum L. Okay. I gave it a special symbol here. I gave it a symbol S. I'm slowing down here because I'm just getting a pop up that my internet connection is unstable. So hopefully my voice will come back here. But think about how you calculate this moment of inertia here. Moment of inertia is, let's see, it's a mass times a radius squared, right? And you sum up all the masses in the thing as it rotates around. So you take a piece of mass right there, there, and really those masses are just individually making orbital motion about the axis of rotation, right? And then of course, omega, let's see, I always have to think about omega. It is the velocity over the radius, right? R is equal to S is equal to R. Yeah, so that's right. I always want to multiply those two, and I suspect you do too. I look at the units. Okay, V has units of meters per second divided by meters. That's per second, which is radians per second. So we're good to go here. Any event, if you multiply these two together, you just get M times V, and that's momentum, and then one of the R's cancels, and so you're multiplying by R. And so this S here that I'm talking about is just the same as R times P crossed with P of each particle moving about the axis of rotation that the thing is spinning on. So calculating I and then calculating omega takes you to the special, the same equation. There's nothing special about this one, okay? Now, but there is something different about quantum mechanics. We talk about a electron. Quantum mechanical spin, we say it is intrinsic. It is just something that the particle has that we really can't explain with classical reasoning because we think electrons are structureless points. And for the longest time, scientists tried to go the other direction. They tried to figure out, well, what is the size of an electron? And, where is the charge distributed on an electron? Those of you that have taken the advanced electricity and magnetism class or plan to, that's one of the kind of classic sort of problems we do when we're figuring out potential of spinning charged objects. We're really repeating some of the problems that people did in the early 1900s after J.J. Thomson discovered the electron to try to figure out, well, what was its structure? And today we're back to it's a structureless point. Now, maybe over the course of your lifetime, research will be done and we'll find out that the electron actually does have some structure to it. I suspect I'll die before that's known. Okay, but that's the way we think electrons are. We think they're just so small that we perceive them as point objects that have no structure, and so because of that, there is no radius that you can calculate an angular velocity over or a moment of inertia over. And so spin, we just say, is intrinsic to an object. Now, I need to just put some equations in place. And the good news is none of them are new. And this is, if I was doing it, well, there is one new, and I'll do that problem here in just a second. If you recall, when we were doing angular momentum last Wednesday and Friday, we looked at commutation relationships, which we had worked with, and I suspect we spent most of the time working with commutators when we talked about the simple harmonic oscillator potential. And we spent some time with it in chapter 3 when we were talking about generalized uncertainty. But all of a sudden in angular momentum, it became a real important part of solving the angular momentum of an electron moving around its nucleus. Okay, so we had these 3 commutation relations. The components of angular momentum don't commute. Okay, and therefore they have a commutation relationship, and it's that right there. And if you stay cyclic, it's just IH bar times the missing component of angular momentum, right? Well, for spinning electrons, we've just replaced L with S. It really is that simple. And we say now that spinning portion, like the moon spinning on its axis, it also has components of angular momentum. And if you commute the various components of that spin angular momentum, you get exactly the same relationship. IH bar times the missing component, as long as you stay cyclic. By the way, for both of these, if you go anti-cyclic, like I go Y then X, I go backwards from XYZ order, or YZX or ZXY. If I deviate from that order, you just inject a negative sign. So there really are 3 missing commutation relationships on both sides of this Washington College colored arrow here. Okay, so that was that was a big deal. There were some other commutation relations we looked at, but I think these are the big ones you're going to be looking at. One of the things we did with these commutation relations is we looked at the eigenvalue problem for the square of angular momentum and the z component of angular momentum. And be clear, we could just have easily have picked the x or the y components of angular momentum. They're just more complicated. The z component of angular momentum in spherical coordinates only depends on a derivative with respect to the variable phi, because that's the variable that changes in the xy plane, which is what happens when something spins around its z-axis. That's the variable that changes. So we focused on g just for simplicity. But both of these operators, the angular momentum squared, okay, and the z component of angular momentum, have eigenvalue equations. Okay, there is the eigenvalue for angular momentum squared, and there is the eigenvalue for the z component of angular momentum. Okay, and this is the kind of the cool part that we came to on Friday of last week. The eigenfunction for these 2 operators is exactly psi, the same eigenfunction that we had previously used for energy, okay, for the Hamiltonian. And you may say, oh, of course it is. Well, it was in modern physics, because I just kind of I said it was, and I suspect Campbell did exactly the same thing for those of you that had him for modern physics. There really was no reason that it had to be, okay? The eigenfunctions psi are associated with the Hamiltonian, because that's Schrodinger's wave equation. There's no guarantee that it would work for L squared. And in fact, in chapter 3, we showed that psi doesn't work for the position eigenvalue problem with the position operator, or the linear momentum eigenvalue problem. Okay, I'm popping up as internet connection unstable again. Any event, hopefully we're good. That is the eigenvalue. We showed, well, when we did the separation of variable techniques, that L had to be an integer greater than or equal to 0. When we did the algebraic solution, another possibility pops up. L could be a multiple of a half integer as well. Well, full integers are also multiples of a half, but we didn't use those 2 guys with angular momentum when we were, or energy, when we were solving Schrodinger's equation. It only came up with the algebraic solution to angular momentum. They don't come up in energy, okay? The half integer guys, okay? And so the question I think I left you with was, are they an artifact that is just in the math that we just throw away, or is there some use to them? And today we'll talk about the use. Now this M, we showed, I mean, remember L was a separation constant in the separation of variables technique. M squared was also a separation constant. We showed that it takes the values from minus L to plus L. Okay, and now that could be from, say, minus 1/2 to plus 1/2, right? You would just go minus 1/2 to plus 1/2, and that would be it. You know what? Nope, that's good. So minus 1/2 to plus 1/2 could be the values of M. All right, and then there was this raising and lowering operator we talked about with angular momentum last week, and it has the same raising and lowering operators. Oh, I don't think I made the point. You should see it, but I can just replace S squared here. I do have a different eigenfunction though for the S squared the angular momentum of spin squared. It's a different operator. Okay, it's a different eigenfunction, I suppose, for this operator than psi for this function. And so that's a difference. And I'll talk about what this means here, what this notation means. And z component of angular momentum, spin angular momentum, I'm just going to call it spin from now on, has its own eigenfunction as well, other than psi. But I think the eigenvalues look very similar. You replace this spin for s, and there is an m here. Now, I should tell you, this m is different from that m, and our author uses them interchangeably. In other references, you'll see this one called like m sub s, perhaps, okay? Just to denote it's different. This m is going from minus s to plus s. This m goes from minus L to plus L, and they have different meanings, okay, different uses. And so our author doesn't put the subscript on it. Griffiths avoids that. He does say in a footnote that he recognizes he maybe should, but it's in a completely different chapter, and the two won't be intertwined, okay? But, and this is where I was getting ahead of myself, there is a raising operator for spin and a lowering operator for spin that are defined exactly the same way. They're the complex conjugate of each other, and it's just the two components, x and y, of the spin, okay? This is the equation that I had not talked about when we spent 2 days on angular momentum. We need it now, unfortunately, for spin, so I have to address it. I didn't need it to get through everything we needed to do in angular momentum of the electrons about the nucleus, but now we're going to. So I just want to show where this comes from. And you know, you can kind of see right there in that eigenvalue, which is L squared with an H bar squared, this part of it, I think, makes perfect sense. Okay, that, you know, the raising and lowering operator is somehow going to have that in it because, well, L squared is x squared component of angular momentum, the y component of angular momentum squared, the z component squared. So it's kind of logical that you're going to see with those two, you're going to see something like that. I mean, it's expected, but we could do a little bit better than that. Griffiths actually makes this a problem. I'm going to work here through problem 421. Okay, these are the equations that that we're going to be using to show that this square root of L plus 1 minus M plus 1, or M minus 1 if it's the lowering operator we're looking at, that those are, I guess, well, I would call these, come on, back. Oh, I got to go over here to go back now. That if you set up, come on, back. If you set up a eigenvalue equation with the raising and lowering operators, which is what we're doing here, okay, I don't too much care what the eigenfunction is, but I do want this to be the eigenvalue. Okay, and I want to show that that's true. It's probably believable. I could probably just tell you to believe it, but it's better to prove that it's true. Now, one of the things we will accept is that since angular momentum components are real observable things, you can measure them in the lab. Well, that means that their operators must be Hermitian operators. Okay, if you can take a Hermitian operator and measure the component associated, I don't want to say component, measure the quantity associated with that operator in the laboratory, we've always said, and we kind of leave it as we proved it, but we did it for every example we knew. That means the operator is Hermitian. Okay, energy is a Hermitian operator, and that's why you get because you get real energies when you measure the thing in the lab. You don't get complex numbers for energies, which was a question somebody asked me. It's a good question, actually. There's no reason to expect it has to be, but that is one of our postulates, is that if an observable exists and there's an operator associated with it, that operator is Hermitian, okay, and it gives you real eigenvalues. In any event, so we're going to assume without proof that Lx and Ly, the x and y components of angular momentum, they're Hermitian operators, okay? And I guess the other thing I want to then decide, and you may just be willing to accept it, if the x and the y components of angular momentum are Hermitian is a linear sum with a constant, the square root of -1 or minus the square root of -1. Is that also a Hermitian operator? Are these raising and lowering operators also Hermitian? And you might just accept it, but that's the first line right here. I'm showing, and this is the kind of thing you had to do on the third problem of the second midterm, showing that an operator is Hermitian. Essentially, you have to show that this guy, okay, is the same. Okay, let me find its partner, is the same as this guy, right? Because if those two things are the same, then we say the operator is Hermitian. Okay, and some of you were a little less than crisp on your logic in that, but I think I was pretty liberal in grading the third question. If you made some point of this, well, you win and you get most of the points of the problem, if not all. Anyway, I just substituted in. Actually, Griffiths just substitutes in. I'm taking this right out of his solution. The x component plus or minus I, y component. I just made use of that to substitute in for that. Okay, and as we said, I think the components of angular momentum themselves, we're going to accept are Hermitian. And so that means I can take the x component, the y component that used to be operating on G, swap them back to operate on F because they're Hermitian, okay? And then I just left the plus or minus I. And then I can, I guess, reorder. I can combine. And so I've got these guys right here. But notice that the plus or minus sign gets reversed to the minus plus sign in front of the I, because as soon as you bring this constant into the bra portion of the bracket here, okay, it is the complex conjugate, and so that's why that order has to be flipped, right? I'm taking the complex conjugate right there, and then I just substitute back in the raising and lowering operators, and it becomes the lowering and the raising operator, I guess, okay? And they are the adjoint of each other, I guess, which makes them Hermitian, okay? And so that's so we're good to go. And so we've shown that the raising and lowering operators, I guess, are Hermitian operators. All right. Now, there was an identity. You will run across it on the worksheet that's due Wednesday if you've forgotten it. But actually, I think I had it solved for L squared. I've rearranged that identity in order to solve for the plus minus operator as a pair here, okay, as a product. And so I'm going to let that operator, the plus minus or the minus plus, I guess, whichever order. And I always hate when you do this, but hopefully you can follow it. If you don't like it, just do the top symbol, the minus and the plus on the top row, and just realize it flips around with the bottom row. Okay. In any event, I'm going to let that operator operate on the eigenfunctions for the raising and lowering operator. Okay. So I plug in that identity. Okay. And then I just do the operation. And L squared, well, that's the eigenvalues for L squared. LZ squared, remember, is H bar M. Square that. There's a negative sign right there. And then I guess this is H bar times the Z component operating once. So it's H bar times just MH bar. And so those are the three terms you get when you use this identity right here. And you're finding, I guess, the expectation value of that thing. Okay. All right, great. Let's see. What do these are all constants, right? All constants. So they can all come out in front of the bra and the ket. And that's what I'm doing here. And the H bar squared has been factored out. And I've left with that. And I think that is just one. That should be the Dirac delta. As long as M and L are the same, that's just one. Okay, and so we've decided what is this expectation value, and the answer is it's that. Now, here's the clever part, I guess. We've decided that these raising and lowering operators are Hermitian, right? And so that means when I did this right here, look, I can bring one of them out there by virtue of this, and that's exactly what's been done here, right? And so I guess, well, what is that guy right there? Let's go to the raising and lower operators eigenvalue equation, where these things are the eigenvalues and have yet to be defined. Remember in the previous slide, I'm trying to find what those eigenvalues are. So let's do two cases, one when we're doing the raising, one doing the lowering. We'll call the raising coefficient A, the lowering coefficient B. What we're going to do is that, which we know to be that thing right there. Okay, that thing that I've underlined, that grouping of the constants right here. Okay, so great. We do the upper sign. We have that thing right there is equal to that thing. And then I'm making use of the eigenvalue equation with this unknown A here. And ultimately, those guys are orthogonal, so you can bring out those constants. It's just multiplying by its complex conjugate, right? That's A star, okay? And L and M are just, they're the same here. And so since they're orthogonal, those two guys go away, and I'm just left with this guy is equal to all of that. And of course, this was the positive one, so the positive one is using that sign right there, right there. Okay, so that tells me that that's true for the eigenvalue for the raising operator operating on some eigenfunction. I can do the same thing for B. It's almost trivial to redo it again. The only difference is I've got a negative sign because that's what came in right here, okay? And so I think we've shown, as I needed to, that this is true, that the eigenvalue, either the A or the B, is that guy right there. And then what we're going to need it for in spin is to set up this relationship right here, that if I take the raising and lowering operator on a spin state, I get that same thing. S places L, and this is really an M sub S replaces M. All right, so we're good to go. We've got that ready to go. I said that spin was an intrinsic property of particles, and this little chart here talks to what is the spin for various particles we encounter in physics, modern physics. Pi mesons, they're kind of an exotic particle. They actually have spin 0. Most everything we're going to think about, it's all quarks and leptons, which if you think about common materials we run into, like atoms, that's all we got. They're all spin 1/2 particles, okay? Photons, another kind of common particle that has spin 1. Some of these other exotic particles, delta baryons, and even gravitons are said to have spins 3/2 and 2, intrinsic. We don't know why. It's just experiments have shown that that's what they turn out to be. Spin's fixed for a particular particle, and while the orbital angular momentum quantum number can take on any integer value, and transitions between states happen anytime you perturb it, once you got a spin fixed for a particle, because it is a particular particle, it doesn't change. Okay, so completely different from orbital angular momentum. Spin angular momentum is fixed for a particle. Here's something on notation. Okay, I said the state in lieu of psi, which is the energy eigenfunction or the orbital angular momentum squared eigenfunction, or the z component of orbital angular momentum eigenfunction. For spin, we write the state this way. And it's a little bit silly because S here is always 1/2, okay? And we think there are two spin states, spin up and spin down, okay? Informally, people use up and down arrows for that. In the more formal notation, I said that's S, okay? And remember, M here could be either minus S or plus S. Half integer values were okay. And so you can either have that value of M or negative 1/2. Those are the two possible values. Okay. And so when we write something like this for the spin up case, this is what we mean: 1/2, 1/2, or 1/2 minus 1/2. The symbol that people use as a shorthand is this Greek chi. It's the Greek letter C, Charlie, and then a plus for the up state and minus for the down state. And you've seen these before: 1, 0, 0, 1. We call those two element column vectors. They're referred to as spinners. And so the spin state of any 1/2 spin particle can then be represented as A and B. The two kind of bases are 1, 0 and 0, 1. And so I can get any other state by just going some constant times the plus state, okay, and a different constant times the minus state, the down state. Okay. And so that's our notation. And we use it interchangeably. And you're going to see me do that here as I work through. And I think I'm working now through the worksheet on spin for the next 10 minutes or so that I got left. I need to find what the matrix operators are for S squared, uh, SZ, the raising and the lowering operator. It seems to me they all have to be 2 by 2 matrix. And let's see if we can make sense of why with an example. Okay, and so I said S squared as an operator, the square of the spin's angular momentum, unstable internet connection, and I'm just going to operate on the plus state. I leave you to operate it on the minus state, and we'll see how we work out these elements. So I go S squared that's the formal way of writing it. And remember the eigenvalue for this, S squared, surprised I didn't put it on here, was equal to H bar squared times S plus 1. And then I guess both of them are operating on the state, which I'm going to be too lazy to write 1/2 and 1/2 here. Okay. And so I put spin is always 1/2. So this is almost silly. 1/2 plus 1, that's 1/2 times 3/2, that's 3/4 H bar squared. And again, I'm operating on the plus state. So I went like that. And so it seems to me it's 3/4 of H bar squared times the plus state. Okay. And that's kind of an energy eigenvalue problem, isn't it? It's just like an energy eigenvalue problem. It's the S squared eigenvalue problem. There's my eigenvalue. My eigenfunction in this case is the plus state. All right. So now we're left trying to work out what are the matrix elements of the matrix operator representing spin. Now I've already used A and B for the spinner states, right? So I went C, D, E, F, which follows Griffith's notation. And we just said that S squared operating on a plus gives us this. This is similar to what we did to find the eigenvectors when we knew what when we knew what the matrix was, only now we know what the eigenvectors are, and we're trying to back produce what the matrix is. So it's kind of backwards of the second problem on the midterm 2. I don't know these guys, but I know it's 1, 0 because I chose to work out S squared on chi plus, the upstate. So if I take that, multiply it by that, let's see, C times 1, D times 0, E times 1, F times 0, that's CE. And we know, because we worked this, that's that guy right there. That's 3/4 H bar squared is an eigenvalue times the upstate. And so that tells me exactly what C has to be, right? C has to be that, and it tells me what E has to be. Okay, so on the worksheet, this is problem 1. I'll leave you to work out what S squared is on the minus, do exactly what I did here. And so you ought to be able to figure out what the elements D and F are. Here's the answer. The answer is going to be 1, 0 when you get it right. And of course, I factored out the 3/4 H bar squared. And so interestingly enough, the angular momentum, spin angular momentum, the S squared matrix operator is an identity matrix with that as a constant out front. Kind of neat that it works out that way. Let's keep moving here, okay? And this is, I guess, problem 2 on the tutorial. Now we're working out the Z component of spin. And did I have this on the last slide? I did have it. Why did I rewrite it right here? It was right there in front of me. I'm getting old, can't see. I wrote the eigenvalue equation with the right eigenfunction, okay, which we said notationally. We're going to do the plus state. I'm going to leave you to do the same thing. That should be more of a subscript, but you're going to work out the Z component on the minus state, and then you'll get 2 other elements here. But in any event, this is a little bit different. Yeah, it's close enough. 1/2, 1/2 is the upstate, right? And let's see, H bar times 1/2, H bar times 1/2 on the upstate is equal to 1/2 H bar. And I just wrote out the other way that's more useful of the column vector for the upstate 1, 0. Okay. And so I guess that tells me that the Z component of spin operating on the upstate spinner eigenvector is equal to 1/2 times the upstate spinner. That's good. Okay, again, we're trying to unmask what the 4 coefficients, the 4 elements of the matrix that's associated with SZ. Let's see, I was up to A, B, C, D, um, E, F, right, on the last one. F, G, H. I didn't do I just because I looks like a square root of -1. I went J and K, okay? And our job is to get these elements. Well, from this result right here, okay, if I operate this guy on the upstate like I just did, let's see, I get G times 1, H times 0, G, J times 1, K times 0, J. And that we just decided had to be 1/2 H bar over 2 times the upstate. And so you can see right away that guy right there has to be G. And of course, J is equal to 0. Okay. And so I factored out the H bar over 2, and I'm left with just 1, 0. You get to work out the elements H and K, okay, on problem 2. And you're going to find they're 1 and 0 and -1, but that's the deal. Okay. Now, one of the things that's interesting about the Z matrix, we specifically believe, and you can kind of see this here from the result of um, the second problem on the second midterm. Once you got the matrix in a diagonal format, you'll notice that you should have noticed that the diagonal elements were the eigenvalues. And I think some of you probably went, whoa. I actually had somebody write that, like, whoa, look at this. And a couple people predicted it when they found the eigenvalues before. Anyway, you see that's what's happening here. It's H bar over 2 minus H bar over 2. The Z component of spin must have well, its eigenvectors are showing up here as the diagonal elements. So these eigenspinors, the plus and the minus guys I talked about, must be the eigenvectors for the Z component of angular momentum. Okay, and that's kind of a backwards logic, but it is true. All right, a couple more, and then we'll call it a day here. Now I want to do the raising and lowering operator, and I think I'm going to work out the raising operator completely. Yeah, and this is problems 3 and 4 on the tutorial, and you'll be left to work out the lowering operator for spin. Okay, and this is that equation that I proved with in problem 421, what are the eigenvalues of the raising and lowering operators. And one thing to remember about the raising operator or the lowering operator is, and I don't know that I said it specifically, it was on the page, but I didn't point it out. But remember, what does a raising operator do? It raises the state up by 1. What does a lowering operator do? It lowers the state by 1. I don't know that I was, in fact, I know I didn't specifically make that point when we went through that problem, but it is true, right? Okay, so that makes kind of an interesting result. If I take the raising operator on the upper spin state, the spin up, well, there is no state above that. So your expectation should be that the answer should be 0 for that. And I worked it out rigorously here using all the notation. So I'm doing the raising state on this guy right here, and use this full equation. H bar's out front, 1/2 times 3/2 again, right? S and S plus 1. That's always going to be 1/2 times 3/2. But now this, I'm subtracting off 1/2 and 3/2. So I'm subtracting off exactly those two things, and that's why I get 0 right here. Okay, so, but that's what you'd expect. You could have almost written that down by inspection. You do the raising operator on the higher state. There's no place else to go. When we're talking about ladder operators, you're at the top of the ladder. There's only 2 rungs on the ladder in this case. On the other hand, if I do the raising operator on the lower state, okay, lower state means negative right here, minus 1/2. S is, the first one's always 1/2. If I do the raising operator on that, that's always going to be 1/2 times 3/2. But now I'm subtracting off minus 1/2, and then if I add 1/2 to 1/2 to that, it becomes positive 1/2. And so what is that? That's 3/4 minus a minus 1/4, which is just 1. And so that's why I get the H bar right there. Okay. And so that's how the raising and lowering operators work on the 2 spinners. Actually, I just did raising operator on the 2 spinners. I get those 2 values. And now I'm just advancing. By the way, you don't have to do this. If you want to go like A, B, C, D each time when you're doing your tutorial, that's just fine. But I did advance the letters to N, O, P, and Q for the operator, for the raising operator elements. And we're operating on the spin state upper. the upper spinner, the spin up. And let's see, N10, O times 0 is N, P1Q0 is P, and that's 0. So apparently both N and P have to be equal to 0 in this raising operator. On the other hand, I took this result right here, and I said, well, what if I operate on the lower state, which is this guy, right? Okay, and I do want to make sure that it wasn't lost. Yeah, because I kind of glossed by this. Notice here was minus 1/2, right? And because of this thing, it became plus 1/2 right there, which I wrote as 1/0. And that's key. It's an easy thing to overlook because you just get in the habit of using the same state. On this guy, notice the minus went to a plus because you operated with a raising operator. And so while you're operating initially on the down state, when you do the eigenvalue equation and you bring the H on, you're operating on the up state. And that was exactly because of this fact right here. Okay. So in any event, this kind of, it could cause you to get a math error, I suppose. It tells me that this O component, right, N times 0, O times 1, P times 0, Q times 1, OQ, is equal to H factored out of a 1/0, which is the up state, right? Where you started with the down state. And I should probably not use arrows to point now because I mean them to be states. Well, that tells me that O is H bar and Q is 0. So I've unlocked all the elements now with this bit of logic and mathematics. And I guess that means, fill them in here, N H bar factored out, 0 and for P and Q, and so that must be the plus state. And you should show with number 3 that when you work out the minus, it becomes this. All right, one last thing and we'll wrap it up. How do I get SX or XY? And remember that we have the raising and lowering operator written as this for a reason. If I add the two guys up, I get the raising and the lowering operator together. The complex part cancels when I add them up, and I get 2 times S. So SX is equal to raising plus lowering divided by 2. And so I just took those two elements, the one that you're going to show and the one I just showed, I added them together, and I divided by 2, and I find that the operator is just that. Okay, just do 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, good to go. Factored out the H bar, and then I had the 1/2 out front. And so that's S sub X. You're going to do exactly the same thing to find S sub Y. We already did the Y component of spin. That was one of my example problems back in chapter 3. And I just said, don't worry about why it is, it just is. Now you can see where it came from. It came from right here. And you're going to work that one out in step 5 on the tutorial. Okay, the one thing that is a shorthand people do, I've got these 3 answers right here for X, Y, and Z. And I've worked out this one and parts of this one right here. You're going to do this all to yourself. What people do is they factor out, and the guy who did it, the people who did it was Pauly. He said, hey, I can factor out the H bar over 2. It's always there. And we have this notation. These things are called the Pauly spin matrices. And if you take the Pauly spin matrices multiplied by H bar over 2, it gives you the spin operators that you need, the components. I think I'm over by a couple minutes here, maybe about 4 or 5 minutes. I better quit right now. Are these operators Hermitian is a question. Check it. Flip them around. Take the complex conjugate. Yep, think they are. That's pretty easy to flip. That's pretty easy to flip. They're real numbers. They're their own complex conjugate. So I think the answer is yes. All these guys are Hermitian operators, and that's handy. They better be observables. And so that's what we'll be talking about on Wednesday. We'll see, okay, if you make a measurement of these spin components, what are you going to get? And so that's the topic for Wednesday. Hey, that's all I got. I'm going to stop sharing. Any questions? All right, then they're out of here. I see them leaving. They must be hearing me. You all have a great day, and we'll see you on Wednesday.